Alright, in this video we will be learning about the concept of energy and how to use the conservation of energy to solve physics problems. You'll find the problems that we've solved before can sometimes be solved much easier using the concept of energy. What energy is the ability of something to make a change in itself or another object. And it can come in many different forms. For the physics problems that we're going to be working on right now, we're going to deal with three different forms. Those three forms are gravitational potential energy, which is the energy that something has because of its position in a gravitational field. So most of the times we're dealing with Earth's magnetic or gravitational field. And so that's equal to the mass times the value of g, that 9.8 meters per second squared, times height. When you multiply all those together, you're getting weird units of kilogram meters squared per second squared. What we do for energy is we just use the unit of joules for energy, and that's abbreviated with a capital J. Kinetic energy is the energy something has because of its motion, and that's equal to 1/2 mv squared. The work is a way of going from one form of energy to another form of energy, and that's equal to the force times the distance moved. It should be noted that only the force that's in the direction of motion is doing that. So if, for example, if you have a wagon and you're pulling a wagon with a force at an angle this way, and the wagon's going to move to the right, only the component of the force that goes to the right will be used in determining the amount of work done. So the force has to act over a distance. These forms of energy and other forms of energy all kind of play together, and they can change from one form to another. But what can't happen is energy cannot be created or destroyed. And so at the bottom here we've got the law of conservation of energy, which is very important, which says that the work that we put into the system plus the kinetic energy that it has initially, plus the gravitational energy that it has initially, equals the work you get out of a system plus the kinetic energy that the system has in the end state, plus the potential energy that the system has in the end state. Looking at a couple of different illustrations of this, first with a bouncing ball. Let's see where that is over here. Okay, so I have a ball, and right now you can see the ball sitting on the ground, so it has no potential energy. It's not moving, so it has no kinetic energy. If I pick this ball up, you can see the potential energy increases, and if I drop it, the potential energy decreases, but at the same time the kinetic energy increases. So they trade off between the two. The amount of energy you can see is slowly going down because that ball is not a complete system. Some of the energy from the ball hitting the cement is going into the cement, but it takes some time. If I take that ball, instead of dropping it on the cement, if I drop it on the wood, you can see that the amount of energy that gets absorbed is a lot faster than how quickly it goes into the cement. And finally, if I drop it into the styrofoam, you can see that very quickly the styrofoam absorbs the energy. So when I have collisions between things, collisions are said to be either elastic or inelastic. The collision between the ball and cement is actually fairly elastic, meaning that not much of the energy goes into warming up the materials as they're colliding and deforming the materials. Whereas when I drop the ball on styrofoam, a lot of the energy will go into deforming the styrofoam, and so the energy doesn't stay with the ball very much. Another simulation good thing to look at is if I take a skater on a ramp. As he goes back and forth, you'll see that because of the conservation of energy, when there's no friction, the skater will always return back to the same level as he started with. Okay, and his maximum kinetic energy will max out at the bottom. So we can look at an energy versus time graph. You can see that as he goes, his potential energy in blue decreases as he goes to the bottom, whereas his kinetic energy is increasing at the same time. So his total energy in yellow stays the same. If I turn friction on, what you'll see happening is that the total energy remains the same, but where did I go? Oh. Well, anyways, the total energy remains the same, but a lot of it starts going to thermal energy. So that's where a lot of our energy goes, is into thermal energy. All right, moving on. So looking at how do we solve problems with energy. The way we solve problems with energy is by looking at the law of conservation of energy and what sort of energy do things have initially and what sort of energy do they have finally. So in this example problem, we have if steel venom is going at 30 meters per second, how high is it going to be able to reach? So if you think about steel venom, the roller coaster, it has a track that goes up, kind of makes a U shape, and then you've got the train that hangs down from the track. So we're saying is this is starting out at 30 meters per second, and it's going this way. We want to know what height can steel venom attain. When we're looking at this, we have to think about in terms of energy, what sort of energy does it have in the beginning? So we go back to our initial conservation of energy, that the work in plus the kinetic energy that we start with plus the potential energy we start with equals the work out plus the kinetic energy we end with plus the potential energy we end with. And we think about all these terms and we say, well, does steel venom have any work being put into it? It does initially to get it going, but in this problem we're not talking about that instance. We're talking about it's already moving at 30 meters per second, so we're not putting any additional work in. Does steel venom have kinetic energy to start? Yes, it's moving at 30 meters per second, so we're going to keep that. Does steel venom have potential energy? Now it is above the ground, but it's not. But this is as low right here. This is as low as steel venom gets. So no, we're going to say it doesn't have potential energy. We're not going to take any work out. That would be like, we're not talking about friction here. We could, see how much friction is, but we're not going to take any work out. It's not going to do any. At the very top, will it have kinetic energy when it's up here? And the answer is no, because if it had kinetic energy, it'd still be moving and it'd be continuing to climb. And so it would have potential energy in the end only. So we're looking at this all simplifies to the kinetic energy it starts with is equal to the potential energy that it has in the end. Kinetic energy is equal to 1/2 mv squared. Potential energy is equal to mg8. You can see the mass of steel venom doesn't matter. We can rearrange and solve for height. And so height is equal to 1/2 v squared divided by g in this case. All right, and I'll let you plug in the numbers and do that yourself. How much force will it take to stop the ride in a distance of 30 meters if the whole train has a mass of 10,000 kilograms? So now we're going to look at, again, work plus kinetic energy plus potential energy is equal to work. So this is work in. This is one over here is work out plus kinetic energy final plus potential energy. So now we're looking at how much force will it take to stop the ride at a distance of 30 meters if the whole train has a mass of 10,000 kilograms. So again, if we're stopping the ride, we're not putting any work in. When we stop the steel venom, it's on that low part, so it has no potential energy, but it is moving, and it's going to be moving, we'll assume, at that same 30 meters per second. So it still has kinetic energy to start with. Are we taking work out? Yes, because we're using a force to stop the train, so we're putting some work out. When we're done, when we're stopped, it won't have kinetic energy, and it won't have potential energy either because it's sitting there at the bottom. So we're left with kinetic energy equals work out. Kinetic energy, again, is 1/2 mv squared. Work out is force times distance. And we're given the distance, we're solving for the force, so rearranging for the force. Force equals 1/2 mv squared, in this case, over the distance. Now again, this equation is not one that applies to all situations. You always have to go back and look at the law of conservation of energy to know whether or not these apply. Okay. We'll be doing a lab where we look at how high you can jump in terms of like what sort of energy you have. But just to kind of go kind of crazy, let's look at what I like to refer to a situation called the one Snickers jump. So we're going to pause here for a second. We're going to watch a video of the one Snickers jump, and then we're going to come back and we're going to do some calculations with the one Snickers jump. First, the normal jump. Then she eats the Snickers. All right, so now we're back, okay? And we want to know how high could you jump if you only use the energy in one Snickers. So one Snickers, at least I think a fun-size Snickers, if I looked that up correctly. Let's go back and check that indeed I was looking up a fun-size Snickers because, yes, calories in a fun-size Snickers. One candy bar has 80 calories, okay? So one fun-size Snickers is equal to 80 calories. Now, in calories with a capital C, there's a difference. 80 calories is equal to, well, we got to convert that so we can use something that we can use in physics. We wanted to put it into joules. So there are 4,184 joules in 1 calorie. Okay? So to find out how many joules we have, we take 80 and multiply by 4,184, and we find that that is 33,000. Again, let's just keep with 2 significant digits. So 330,000 joules. Now we're going to look at, well, how high can we jump with 330,000 joules. So if we have that energy put in, that's going to equal our mass times G times H. So let's say our mass is about, we'll go with about 60 kilograms. Sounds like a good mass for a person. 9.8 meters per second squared for G, and then H. We find with that jump, you could get 569 meters, so we'll round that to significant, 570 meters into the ground, or up above the ground. So that's a pretty substantial height there, okay? If we look at how much force would that take, to put in the amount of work it would take to equal 330,000 joules, you take work as force times distance, so the force you'd have to use. Let's say when you jump, you got to bend down and then jump back up. Let's say you're able to bend down with your knees half a meter. To bend down half a meter, you would have to get that to be 330,000 joules. The amount of force that you'd have to get out of that would be, divide that by 0.5, would be 660,000 newtons. Okay, so that's a pretty substantial amount of force. Just to put that into pounds to get a better idea of that, that would be 145,000 pounds. I don't know about you, my legs are pretty strong, but I don't think I could lift 145,000, oops, not newtons, pounds. Okay, that would just be insane. So your legs would have to be really big. Now, strength is proportional to the radius squared of your legs. So if you look at, maybe I could lift 660 pounds with that. So that'd have to be 1,000 times stronger. So know how much bigger my legs would have to be? I take the square root of 1,000. So that means my legs would have to be 31 times the size that they are now to be 1,000 times stronger to complete this jump. Okay. Well, hopefully I've done my math all right. I'm running out of time, and we can maybe work out some other weird energy scenarios in class.